image here, we are showing spatial domain, and that's the frequency domain. So in frequency domain images, I will show later on even some theoretical derivation about why we have the same size in the frequency domain as the input image, but then it looks completely different. So yeah, so we have covered different types of spatial domain operations, and this lecture is to give you a brief background about the frequency domain. So I think most of the techniques we introduced today is not exactly for you to do some development. That's probably beyond the scope of this lecture, but it's mainly for conceptual understanding of many of the image processing techniques. Because when you consider images, they are pixels, but on the other hand, if you look at it from an entirely different perspective, then images are a combination of different frequencies. So that different perspective is very useful sometimes. So I will show you some examples why they can be very useful. Okay. Okay, so here are the topics for this lecture. We will describe the basic principles of Fourier transform, and then based on the frequency domain, how we do some processing. So mainly it's still about image filtering, because once you have different frequencies, we can consider whether we want to filter out certain frequencies, and that would give different effects on the image. And then a little bit further from that is we can do multi-resolution processing, and here's just with some kind of examples. So we start with motivation, like when we talk about frequency in the simplest term, or from intuitive perspective, what are frequencies? So if we consider if you have an input image, and then we can do a downsampling. So downsampling means we just resize image to, in this case, it might be like a quarter of the original image size. So typically, how we do this? So typically, you can just do like sampling. So every 4 pixels, you choose 1 pixel. So that is one way. Another way is you can do averaging. So every 4 pixels, you average them. Then you get 1 pixel to replace the 4 pixels. So that's the simplest way if you don't do anything too fancy. So you can do that kind of sampling. So once you have the downsampling image, if you look at just this image, it might look very much the same as the original image, but if you try to do another upsampling, then you will see a huge difference between the upsample image and the original image. So when we do upsampling, we do the reverse process. So from 1 pixel, get 4 pixels. So then there's also various ways to do it. The simplest way is you just duplicate that 1 pixel into 4 pixels. So what we get here is a blurry version of the original image. So the most intuitive explanation is when you do downsampling, you are losing information, right? Because you are choosing a subset of the original pixels, or even if you do averaging, is also you're reducing the kind of information in the image. And when you do upsampling, you have no way to get the information back, because you already thrown away all those information. So there are more complicated ways to do the upsampling. So for example, there is a technique, very specific technique, that's called super resolution. So that means if we go from a low resolution image, remember we talked about spatial resolution in first week. So from a low resolution image, that means a smaller image, then you try to go up the resolution level to a bigger image. So that's called a super resolution. And we have pretty smart or deep learning ways to do it. But if you just do the basic duplication of pixels to get back the original size, you don't get back the original information. And what's lost here is mainly the high frequency information. So that means the details in the images, the structures, like how the tree, the branches, the leaves look like. Those are the detailed information in the image. So those kind of information, because when they are detailed, that means you have smaller pixels to represent a certain region. So when you do the downsampling, you are removing some information. And then you lose those details. So that's the very intuitive explanation of what are the high frequency details or the high frequency information in the images. So when we talk about high frequency, we talk about edges and even noise. If you have lots of noise in the image, those are high frequency. So that means from one pixel to the next, the neighboring pixels, you see lots of changes. So that means the rate of change is high, so that means the frequency is high. So that's the kind of definition. So like in your lab, when task 3 maybe, when we talk about you have different types of structures in the images, so and of different frequencies. So you would consider what is the background. The background is it's quite smooth. So that means the rate of change across pixels is quite low. So those background parts, those would contain mainly the low frequency information. And then the more highly changing regions that are the high frequency high frequency regions. So that's the kind of we in here we were still talking in terms of the spatial domain. So we look at the image, we think about what are the high frequency, low frequency information. So we do have a correspondence from frequency to the spatial domain. But if we switch our thinking to the actual frequencies, so to do that, we need to first talk about the Fourier series. Or if we transform the images into the frequency domain, that's the Fourier transform. And the concept was developed many years ago. That's before we have images. And it was proposed for just any function, especially univariate function. That means functions with a single variable. And Fourier was especially considering about periodic functions. So that means it's a signal. So the signal is infinite. There's from minus infinity to positive infinity, and the signal changes periodically. So if it's that kind of function, his idea is this type of function can be rewritten as a weighted sum of sine and cosine functions of different frequencies. So I will show you an example later. And here is just some interesting information, like when he first proposed the idea, even other famous mathematicians didn't really believe him because it sounds very simple and too general. I think over time, people find there are some restrictions to what functions can be approximated by the weighted sum of sines and cosines, but there are some very small restrictions. So as long as the functions are periodic and they can be differentiated, the kind of requirements are met, then this Fourier series would exist. So what's good about this is here essentially sines and cosines, they are like waves. So any sine or cosine function, they have a certain frequency. So so that means if I have function, then we can use different frequencies to represent it. And this original definition is for 1D. And with images, it's 2D. But we can also view images as you can just repeat the image in the spatial domain. Then that becomes periodic. And then at the same time, you can use frequencies to represent images. So that's the essential idea behind it. And here is a definition of the sine wave and how we can combine different frequencies. Yeah.
I wasn't sure how much the when you select the image has period like 2 pi or something.
Yeah, so images is, image is discrete. There's a fixed range. But in mathematics, when you just try to define it, you can replicate the image to the right bottom, make it kind of infinite. So it's, just repeat it. So yeah, mathematically, when you try to derive these equations, there will be equations later on. You will see we do define it in an infinite space. And that will meet all the criteria. Okay, so here is just a definition of the sine wave. This is purely just a sine wave. So any sine wave, they can look like this, these parts. So essentially it means a sine wave has multiple parameters. So x is a variable, and omega here is the frequency. So a higher omega means higher frequency. And then the phi here is the phase. So that means if you put all the sine waves into a coordinate system, where this dot starts from. So if you start from 0, then the phase will be 0, or if you shift it, then there will be a small phase, yeah? And the A is the amplitude. So that means a bigger A then gives you a bigger amplitude. So that's how we use a more generic form to represent sine waves. So all this can be represented by some form of this formula. And if you sum them together, it will look like something like this. So in this case, it doesn't look that periodic. But if you keep adding more and more sine waves to it, then you will see some kind of more periodic function emerging. And depending on how you design these sine waves and what's the objective of your final function, then you will need to decide how many of these sine waves you need, what are the different parameters you need in order to approximate a certain function. So here is a more, or maybe better example. So we have two examples. So the first one is we want to approximate a square wave. So a square wave means like it's a straight line at 0, and then it goes up straight, and then for a certain period, and then it comes down back. So it's a square, and then the square just keep continuing infinitely. So to get this square wave, we simply just add these sine waves together. We will eventually get something that looks really like a square wave. And so what this is showing here is if it's just one single sine wave, it will look like this. And then we add this one onto this, then it will look like this. And then you add this one, it looks like this. So this part is getting more and more smoother, and yeah. So gradually, it will become more and more like a square wave. And so in this case, we say it will need an infinite amount of sine waves in order to get a perfect square wave. And the reason is because when you change from 0 up to 1, there's a straight line go up, and that means you have if you compute the derivative at that point, it's almost like infinity for that derivative. So then that means we need an infinite number of sine waves to get this square wave. So these are just some mathematical intuition behind it. And this one is just another example about sawtooth wave. So sawtooth wave, if you just approximate this one with straight lines, that is what sawtooth wave looks like. So similarly, to get there, we will need to sum up these equations. And so the difference here is now you can see we are using different, this amplitude is different, and also the omega is different. And you have the minus pi here, and yeah, different parameters. Okay. So here's a summary of the differences. So we consider spatial domain is very straightforward. It's the image itself. Whatever image we see, then we represent them as 2D metrics to approximate what we see in real life. And all the previous processing techniques about spatial domain, those are direct manipulations on the pixels. And depends on how you want to manipulate it, pixel by pixel or neighborhood by neighborhood. But all the operations were done on the 2D matrix or a single pixel. And whatever you get from the output, you will put them back into a certain 2D matrix. So that means changes in pixel position, if you change a certain value in that pixel, then you will see a different image. So that means the changes in pixels correspond to changes in the scene. Yeah, so that's very kind of our way of, typical way of processing images. And the other representation is frequency domain. So what we do is we first transform an image into frequencies, and to do that we use the Fourier transform. And the frequencies represent the rate of changes in the images, like I mentioned with that downsampling, upsampling example. The frequencies, the lower frequency means a slower rate of change, and high frequency means rapid changes in the images. So they correspond to different parts of the images. And so once you do the transform from spatial domain into frequency domain, what you get is actually still a 2D matrix. And that 2D matrix should have the same size as the input image. So with that 2D matrix, we can also call it having a 2D matrix of pixels, although now the pixels in that matrix doesn't really correspond to the actual image pixels. So what those pixels represent, I will describe more later. So those pixels represent the frequency information in the image. So each pixel represents how much information is present in the image that's of that certain frequency. So you will see a kind of a noisy image, and it's even more like salt and pepper noise kind of image maybe. So the black regions means there aren't those kind of frequencies in the image. And if you have certain frequencies in the image, then those pixels will light up. So there will be examples later on. So this also means if you consider doing manipulations in the frequency domain, then we can change the values of certain pixel in that frequency matrix, and then that will trigger changes in the frequency of the image. And that eventually, that also means if you change the frequency, you are changing the image itself. So after all these transform the changes, we can do an inverse Fourier transform back into the image domain or the spatial domain. Then you will see the image now looks different. Okay, so this is another summary of what frequency domain gives you. So you have high frequency information that correspond to rapidly changing intensities across pixels. So some examples are edges and noise. And typically we consider noise is the highest frequency in the image. Just because noise are typically small, so the changes really concentrate on a small region. So that means across the small part of pixels, you have very rapid changes. And the edges is where you go from maybe the background into the object. So there should be a clear change in intensities, and that gives you higher frequencies. A low frequency corresponds to a large scale image structures. So that can be either foreground or background. So if you have really smooth foreground of an object, like the chairs, on the chair itself is pretty smooth. So those regions should be quite low frequency. And why we do this is typically this pipeline. So it's starting from the image. So the small f is the image, xy indicates the coordinates of the pixels. And so we start from an image and we do a Fourier transform into the frequency domain. So frequency domain now we use the big F to represent it, and U and V here indicate the frequency. And so in that frequency domain, we can do some processing. So you can do it all sorts of ways. And for example, if you want to apply the Gaussian filter, what we do is you also have a small h here, another Gaussian function, and do a Fourier transform on it, then you will get the big h representing the frequency representation of the Gaussian kernel. And then in the frequency domain, if we want to do Gaussian filtering, we just do multiplication. So we mentioned this during the last lecture. Convolution in the spatial domain is equivalent to multiplication in the frequency domain. So here, this multiplication is just pixel-wise multiplication. Because these two matrices, we can make them of the same size. So you can just do pixel-wise multiplication. So that gives you the output after the filtering. And it's still in frequency domain. So we need to do an inverse Fourier transform back into the spatial domain. And that gives you the filtered output, the filtered image. So you can display this image and see what's changed in the image. So this pipeline is the standard pipeline for doing image processing if we want to apply filtering. And I will show you some examples at the end of this lecture. There are other ways to utilize frequency domain information. But if we just use this typical pipeline, you might ask why we want to do this. Why not just do it in the spatial domain? Because this one, I think, is very kind of difficult to understand, even the intuition why we are doing this. So the main advantage of this is really just about reducing the complexity of the filtering. Because in the spatial domain, when you do the filtering, it's about convolution. So that means every pixel, around that pixel, you compute a convolution operation, and then you slide the kernel and do another convolution. So if the image is of m by n size, then you need to do these convolutions m by n times. So that could be a lot of computations. But in the frequency domain, you can do the Fourier transform for the image and for the kernel, and then it becomes just one multiplication, so pixel by pixel. So that's m by n times multiplication. So that's a lot less than you do all sorts of convolutions throughout the image. And especially if the kernel is large. So remember the Gaussian kernel, we can have different configurations. So with a very large kernel, then that means every time when you compute the convolution, you have a lot of multiplications. But if you do it in this way, this multiplication is fixed. It's only determined, the number of multiplications is only determined by the image size. So even if you have a very big kernel, you still do this many number of multiplications. So it can be a bit faster in frequency domain. The only overhead is initially you do need to compute the Fourier transform. But with a larger kernel, typically it's worth it. It's quicker this way. But nowadays, with convolutional neural network in deep learning, we just do everything in the spatial domain, just because typically the filters are very small. You will see like 3 by 3, 4, maybe 4 by 5 by 5 kind of kernels. They are small. And also the GPUs, they are optimized for convolution operations. So that's why with deep learning, typically we just use the spatial domain. But I will show you some examples near the end of the lecture, even with advanced deep learning methods, why we want to incorporate this frequency domain analysis. So actually this is becoming more and more popular now. If you follow research trend, especially in like segmentation, this kind of applications, you will see people try to incorporate frequency domain information in many different ways. So it's good to have some understanding about the fundamentals. And okay. So here we come back to some more formal definition of what a Fourier transform is. So the previous one, that equation was only about the basic definition of a sine wave. So sine wave itself is not enough. We need to sum together sine waves, and the actual definition is actually even more complicated, because now we involve this I term, that's the imaginary that unit. But it is this equation. If you consider 1D continuous signal, that is the way to do the Fourier transform. So what it means is this is a signal, the input signal. X is a variable. So then we times it with this term, the e to the power I 2 pi ux and dx. So you do an integral because it's continuous. So we don't do just sum, we do the integral. And so the main useful term you should be familiar with is this 2 pi u. So the 2 pi u here is equivalent to the omega in the sine wave. So that's the frequency. And the others is more about how you, when you do the actual computation, then this one they can be expanded into this term. And yeah, so that's about it. So I'm just showing you this formulation to give you an impression of what a Fourier transform looks like. You don't really need to calculate it. But what's interesting here is, so this whole equation is for computing a single value to get this. So this one is also a single value. That means if we consider this u as the frequency, so this fu represent how much information of that frequency is present in this signal. And when you do this, this is like an integral or sum over the entire signal. So that means if we want to find out if a particular frequency exists in the signal and how much of it exists in the signal, we need to go through the entire signal and do the integral and get you one single scalar value for that frequency. And if you want to analyze from 0 to 2 pi, that kind of frequency, then you need to check that many times to find out what's the value for each of the frequencies. So yeah, so the information I want to convey here is for any frequency, we are integrating all the information in that signal in order to find out how much information is present in that signal with that frequency. So, and whenever you vary this u, you need to do this computation all over again. So every single frequency, every single value, it represents like overview of the entire signal. So that's kind of quite different. So in the spatial domain, it's all individual pixels, and the pixels are quite independent. Although in reality there might be relationships across the pixels, but you can treat each pixel separately. But in the frequency domain, we also have, like I mentioned, we can assume those are pixels, but each pixel is a representation of the entire image at a certain pixel. So the scope of representation is quite different. And okay, so here is just the formula for inverse Fourier transform. So remember in the previous pipeline, I showed we need to do the forward transform. So that's the forward Fourier transform to get you to the frequency domain. And then in the end, you need to do an inverse Fourier transform to get back to the spatial domain. So that is the part for inverse Fourier transform. So for the inverse, it looks almost the same. It's swapping these two and also removing the minus sign here and swapping the variable. So yeah, so that also shows you the original definition of the Fourier series when we say, well, any function can be approximated by the sums of sine and cosine wave. So that's like that one. But now we have imaginary part. Okay, so here are some properties. We always mention properties. So this one, some of them are very useful. Like the first one, superposition. Superposition means in the spatial domain, we can combine two images. So here we are using 1D signal. But if you consider images, it's the same. So it's saying if you have two matrices, you can simply sum them together, right? So you get another matrix, and they represent a summed image of the two images. And if you do that, you can similarly do it in the frequency domain. So that means we do the frequency analysis of one image. Now we understand what are the frequencies present in the image and how much information is present for each of the frequencies. We do it for the two images. And then if we want to know what's the combined frequency information in this combined image, we can also do it separately for these two images and then just sum them together. So that's That's actually a very useful property that we will use later on in the examples. And the second one is translation. So translation, you can try to derive this simply by replacing x with this term, and you will see the FU will become like this. So it simply means if we shift the image in the spatial domain, like if you start the 0, 0 from a different point, then the frequency representation of the image will be shifted as well by this kind of term. And this one we have mentioned many, many times. So convolution in the spatial domain is multiplication in the frequency domain. And so this is the motivation behind why we want to do frequency domain analysis. And the correlation. Correlation we also mentioned last lecture. So with convolution, you flip the kernel and do the multiplication and sum. With correlation, you just don't flip it, just directly do the multiplication and sum. So that typically we use this symbol to represent correlation. So if it's correlation in the spatial domain, then in the frequency domain is this. It's not just multiplication anymore. And this symbol there, that means conjugate. So conjugate means essentially this term, you replace the plus with the minus. So that's what it means. We don't really need to use this anyway. So, and multiplication is a reverse of the convolution. So that means multiplication in the spatial domain is equivalent to convolution in the frequency domain. So you can do convolutions in the frequency domain, and that will give you something equivalent to doing multiplications in the spatial domain. And you can also look into this one. The scaling and differentiation just means if you replace x by this one, you should get something like this. And this one is about derivatives. So then you will have something like this. Okay, so the previous definitions were about 1D signals. And here we talk about 2D. So 2D is just a simple extension from 1D, one variable, to two variables. So we just simply put a Vy here as another term, and dy, and also another integral. So the overall formula still looks the same, but now we have extra v and y. And similarly, inverse transform is still just swapping the variables and removing the minus. And here is some additional information about this e term. So because we have this minus I or I there, so that means if you actually expand this or divide this into values for a certain image, then you will see the 2D representation actually contains two parts. So the real part and the imaginary part. So both of them will look like, well, if it's 2D image, both of them would look like the same size as the input image with some values in the matrix. So essentially what you get is after this transform, you get from one matrix to two matrices. One is R, one is this big I. So it's kind of inconvenient that if you do have two matrices that you need to keep on processing. So typically what we do is we just combine those two into the magnitude. So it's simply this R squared plus I squared, take the square root. So it's element-wise processing for each of the metrics. And then that's the magnitude. So the definition is like what I mentioned last time about the the magnitude for the gradient operations. We always do this. This is another way to call it is L2 norm. So we just do this kind of operation to get magnitude. And this magnitude is typically what we use for, like, during this processing. If we want to visualize what's the intermediate output, we can just visualize this magnitude. And then because we have two terms, just by definition, besides magnitude, we can also get phase. So that's arctangent I divided by R. That's just the definition. Okay, so now we really talk about images. So extending from 2D now to the discrete representation. So in this discrete representation, we still have F and the big F, X, Y, U, V, those are the same. The E term looks pretty much the same, like similar, very similar to this. But now we are replacing this part with an M and N term there. So M means the dimension in the X direction. So X can range from 0 to M minus 1, and Y from 0 to N minus 1. So this M and N essentially means the image size is by M and N pixels. So if you consider this term, the frequency now becomes 2 pi u divided by m. That's for the x direction, and then 2 pi v divided by n. That's the frequency for the y direction. And so after this computation, we get one value for this particular u and v, and then you can index u and v with this range, and then you get the 2D matrix that's of the same size as the input image, and that gives you the output after the Fourier transform. And each value in the matrix, similarly, it just represents how much information is in that image that's of this particular frequency. And it might be easier if we look at this one. So that means this one is not giving you the frequencies. This is still in the spatial domain. So, but it's just an illustration of what these frequencies mean. So that means if we consider both u and v as 0, so that means we try to measure what's the constant, or the 0 frequency. That means constant information that's present in the image. So we can consider, essentially, we are just summing up all the information in the image, like summing up the background or the foreground, the kind of idea. So that's what this image is trying to show you. So this is not really giving you the frequency. It's just a representation of what type of frequency we are trying to extract from the image. But these are all in the spatial domain. The images are in the spatial domain. And this one is you shift x by 1. So that means u is 1, v is still 0. So that means we want to analyze what's the frequency in the image that's across this direction. And also this image is essentially trying to represent a single sine wave. It's a very approximate view of what a sine wave would look like. So remember, the sine wave looks like that. So it goes up, and then goes down, and then go up again. So this one is trying to show you, the value initially is low and tries to go up, and then gradually go down. So that's kind of one sine wave. So that means if we can represent, or we try to cover all the pixels in the image using a single sine wave, Then if you compute what's the correlation between that sound wave and the image itself, then that gives you the measure of how much information is there in this image that's of this particular frequency. So that frequency means U is 1, V is 0. So it's a slowly varying frequency. And then we can increase U to 2, V is still 0, then we have this one. That means now we want to cover this image using the sound wave becomes double the frequency. So we use 2 sound waves to draw across the image. And then we try to see how much that kind of frequency is present in the image. Yes.
So is the main difference between discrete and just like continuous or transform, just your choice of inner product or is it dot product? Maybe I'm misunderstanding, but it seems like the discrete version you're just using dot product instead of inner product.
Not really. It's actually they are the same formula. It's just now the frequencies, they are more discrete. And then, yeah, you're just using the sum instead of integral.
So it's like computationally, you're just taking dot products along the logarithmic columns, right? The sinusoids and cosines. Because I'm not really sure I understand how you take, like...
I'm not sure whether you consider it as a dot product. But yeah, this is multiplication per pixel. All the pixels you need to go through. Yeah. So that's actually the same as in the continuous domain, you still need to go through every single variable. Not variable, but every single value across the signal. Yeah. So there isn't much difference between the discrete case and the continuous case. The actual way of doing the computation is different, but the meaning or the formula themselves are not much different. So yeah, so this one is showing you, so eventually when you reach U is M minus 1, that means you want to find out how much information is there of a very high frequency, and now we are using M-1 sound waves, rapidly changing sound wave, to cover the whole image. And so, yeah, so that's just the representation. It's not like we are really representing the frequencies here. And similarly, if you go down this path, then that's giving you the other direction with a similar change in frequencies. And then in the middle is a combination of U and V. So the directions will change too, yes.
Does that mean that the maximum frequency in the image is directly proportional to the size of the image?
Sorry, can you repeat?
So obviously the transform iterates across the pixels on the image, right?
Mm.
And then the frequencies. So as the image size increases, does that mean that the highest frequency that you can find in the image increases as well?
Yeah. So yeah, so that's exactly right, because this output, the U and V, it depends on the size. So I think an easy way is to consider if you have like 100 pixels in the image, then when you measure the cross-pixel difference, it's like you consider 99 changes in the image. Like from pixel 1 to 2, that's one change. 2 to 3 is another change. So if you do this, if you have 100 pixels, then there are 99 times of changes. So if you have a bigger image, then there are more changes. That means you have more frequencies. Yes.
But so is everything in your frequency domain like a relative measure to each other? Because you said like earlier, like the frequencies used to represent things like intensity or like maybe like the shape or something, right? Or like the details. Like I don't really understand like why the magnitude of that frequency would correlate to the size of the image itself.
Oh yeah, I'm going there. Yeah. So so this is one, I mean, what I just described is why the upper bound, typically, you can consider it in that way, why we use M and N as upper bound. Another more theoretical explanation is there is this theorem called Nyquist sampling theorem. That means if you have like n number of samples in a signal, then you need n number of frequencies to cover all the possible information. So that's another way. So by definition, that's why we need, if we have m by n pixels in the image, that means we have m by n samples we want to cover, and then we also have m by n number of frequencies. So that's the theoretical foundation about why we can use this one to represent it. But we don't really have to use this one. You have other options. So you can increase the number of frequencies. So that means you can have a much, much bigger range, but not smaller than this. It can be bigger. So you can go to 2n by 2n for this size. That's all right, because the formula will still work. You will get the values. But you will see, I will show you later on as well, if you increase the size, you will start to see repetitive patterns. So that means go beyond the m by n, that region, you will see the same frequency patterns just repeating itself to the right or to the bottom, like mirroring an image. So why that happens is essentially because this definition, because there is a periodic computation here with 2 pi u divided by m, because they can be expanded into sine plus cosine the representation. So by definition, this term is periodic. So whatever values you get by deriving from this formula, they are periodic. So yeah, so even if you increase the size, you get redundant information. But the minimum size is m by n. Okay, so that's about it. Here is a more intuitive realization of what this frequency domain represents. So if I really just show what's the output of this matrix, if you have this input image, the output will look like this. So, and if this is an input image, the Fourier transform should look like this. So in this one, what we are showing here is we have these 3 images. They have some patterns, and these are the frequency domain information. And this last image is actually a combination of these 3 images. And then that's the frequency domain information. Okay, so if we look at just the first one, and what it's showing here is probably not that clear in this one. We have 3 dots here, and similarly this one. So all these 3 images, we have 3 dots. One is in the middle, it's exactly in the middle, and then the other 2 are like reflections of each other. So these 2 should be of the same frequency, kind of same frequency, but a reflection. So the actual u and v values, these are mirroring each other. So this is representing what's the frequency component in this image. So because you have these repetitive lines, so there is like a single frequency occurring in this image. And similarly with this, you have lots of lines. That's a very regular pattern, a single frequency. So then you have the frequency information of these patterns. And so in this one, we consider this rate of change across the lines is much higher because from one pixel to the next, when you from black to the next black is quite narrow, so the frequency is higher. And then this one, the frequency is much lower because it takes more time to really see the changes. So these frequency values, they are closer to the center. And these two are much further from the center. So the distance here represent like the magnitude of the frequency. And in these images, the three images, we first consider the three, the middle is where the 0, 0 is. So that means U and V are both 0. So what this dot here is representing is how much information is in the image that's of 0 frequency. And this value should always have some value. So it can't be 0 unless your image is totally black. And why is that the case is just because if you put U and V equals to 0 here, then you will see this term becomes 1. So it's gone. And then it's just this one. So it's just summing up all the pixels in the image. And that's what F00 is. And that's also what this image is trying to show there is with 0, 0, we are just summing up all the pixels. And then that's what you get there in the middle. And then these are the actual, when you put U and V of a certain value, then you will have some value from these. And because these images are very regular, they have very few frequencies, that means many other frequencies, you will have 0 information in the image. And another interesting point you might want to take note is why now we have U and V in the middle. Right? It didn't start from there. So it's just a mathematical trick that we can shift the frequency matrix to center in the middle. And if the matrix actually starts 0, 0 from there, it's just repeating this information. Like here, it will repeat this information by starting from here and there. So because this is periodic, repetitive, so the two matrices, whether you start 0, 0 from here or there, they represent exactly the same information. But it's just, if you put it there, it's easier to realize. We like to see like this symmetric kind of representation of frequencies. Okay, and this one, this image is a combination of this one. So another term we can use is the superposition. So like when I mention a list of properties, the first one is superposition. That means if we combine images in the spatial domain, the frequency domain should be just a combination as well. So that's exactly what's showing here. If this image is a combination of these three, then this one is a combination of these three. And what's nice about this is that shows you another advantage of doing the frequency domain representation is if, for example, you want to remove these kind of lines from the image, then you can simply just remove these two dots from the frequency domain. So that can be easily done. You can just replace the values with 0. And then you do an inverse Fourier transform back to the image domain. Then you will see an image that's like a combination of these two without these lines. So that's kind of a cool way of doing image processing. And if it's just in the spatial domain, I think it will be very, very difficult to achieve this type of goal. Because unless you have this image, then you can do a minus, right? You can just simply minus that one from this one. But if you don't have it, then that's super difficult, because if you want to do a segmentation, for example, to identify where the lines are, and because of all the pixels look like slowly varying, it's actually quite difficult to do a very clear segmentation. Okay. Okay, let's have 5 minutes break, and then we will continue. Yeah.
Let's say I have like a basis matrix, just like matrix for my basis. Like what I was asking earlier, it's like, is it equivalent just doing all your dot product by rows with the basis matrix and then by columns? Like, because it's not, because I thought, yeah. No, but I'm saying like the Fourier transform process, like, aren't you just essentially taking dot product by rows and then by columns with the basis matrix? Like the image? Because it should be separable, right? That means like I should be able to do by columns and then by rows, or like vice versa. Okay. Yeah.
So was that kind of clear, or you still have lots of questions? Okay, if not, let's continue. So the first point, now we are trying to move on from, once you have the Fourier domain, the frequencies, what we can do with it. So now we're talking about low frequency, high frequency, and then the first point is about just a summary of what you get from this frequency representation. So this point I've mentioned before. So just to reiterate, each element in the frequency matrix is computed by integrating all the information from the image. But just because in the formula, to get one value, you need to enumerate all the pixels to get this information. And so frequencies represent another representation of what's happening in the images. So that's essentially what's shown here, patterns, especially repetitive patterns, where you can easily kind of visualize frequencies. Then they have pretty nice correspondence in the frequency domain. And the value of F00, that's a special dot, it contains the total intensity over all pixels of the image. And low frequencies correspond to slowly varying intensities across pixels, and high frequencies correspond to rapidly changing pixels. And noise, so that's the point I mentioned before, noise typically corresponds to the highest frequency. Okay, so that's not absolute. It really depends on what type of noise you have and what's the actual noise in the image. Okay, so this is another illustration about why we could put F00 in the middle. So like mentioned, in the continuous domain, the frequencies will keep like indefinite. So in the image domain with the 2D discrete representation, the U and VE, they can range from 0 to almost infinity as well. It's just they are repeating each other. So visually, you can visualize this as this is one representation of the frequency information, the 2D matrix, from 0, 0 to n-1, n-1. So that is one matrix. And it will repeat itself if you go beyond from 0 to n-1, that range. So this one becomes another matrix, the same as this one, and this is the same as this one. So all the same. So it can just go infinitely to generate a super big matrix. So it doesn't have to be n by n, but because they are repeating, so we just choose n by n. And then you can choose anywhere on this plan, you will have the same information. So it doesn't matter whether 0, 0 is here or there. If you crop here, you still get all the information that's present in one region or one matrix. So for visual reasons, if you want to visualize the frequency information more nicely, then we just put the 0, 0 in the middle. And that's the 2D matrix we normally work with. Okay, so here is just another way of how we mathematically, how we get this one. So simply we can use this operation in order to center the 2D matrix. So put the 0, 0 in the middle. So how to do that? I think it's probably really not intuitive. So we could just multiply the spatial image by this term. So that means at each pixel, we multiply this value So x and y here are the coordinates. So when you sum two values together, they can be either even or odd, right? So if this one is an even number, then you get 1. If it's an odd number, then you get -1. So that means you're just multiplying -1, 1 alternatively onto the spatial image. So if you think about that, you are definitely changing how the image look like. But the effect is after this operation, if you do the Fourier transform on this image, then you will get this matrix automatically. So you don't have to consider how to shift this one into this one. So that's kind of I think it's a very not intuitive trick, but it works because we have the E term, and then if you consider follow all these steps, you would get something like this. Okay, so that gives us all the necessary background we need for doing frequency domain filtering. So frequency domain filtering, essentially here we are going back to that pipeline, the flow chart, where we start from the input image F, then we do the Fourier transform into the frequency domain, and then in the frequency domain we can do multiplications for filtering, and then after that we do the inverse Fourier transform into the image domain. So here is just summarizing this pipeline with a little bit more detail. So first we start by multiplying the input image by this term. So that's the one from this previous slide. So the effect would be we can get the centered frequency representation. So once we have this changed F, now we can compute the Fourier transform using the 2D discrete Fourier transform. So now we have F, the big F, that's the frequency matrix. And so that's the frequency representation of the input image. And concurrently, we need to compute a frequency representation of the filter. So any filter, like Gaussian or the uniform filter or Sobol filter, those type of filter. So you get H. And so with these two matrices, you do a multiplication, so element-wise multiplication. And then you get the GE, that's the output. So that's the output after the filtering. So next is do an inverse Fourier transform back to the spatial domain. And here, because initially we did this, and another step is this one would contain the imaginary component. We just take the real component, and then we need to reverse this step as well. So in order to reverse it, we simply multiply this again, and then you will get the actual image. So here's a visualization of an example. That's the input image. After multiplying this term, you will get this one, right? Totally different. And then with this one, this is the same as the previous image. So now with this, we can do a Fourier transform. So that's the 2D matrix we get of the frequency. And you can see the size of this is the same as this one. And it's just the values. And the center dot here is brightest. It's summing up all the image intensities. And then the other parts are the frequency information. And so that's the image frequency representation. And we multiply with the filter in the frequency domain. And then we get the output. So that's the output after the transformation, after the filtering. And now after the filtering, we have this one, the same as previous one. So we just do an inverse Fourier transform and reverse this part. So we get the filtered image. So if you compare these two, this one is blurrier because in the previous one, we were using this filter. So this one, to me, looks like a Gaussian filter. What it's doing is these parts are bright. That means we are passing through this information. And the others, because it's multiply, that means we are filtering out the other parts with 0. So they are masked out. We are only keeping information in the middle. And this is having some slowly varying weights. So this region is a low frequency part because in the middle is 0, 0. That's the lowest frequency you can get, is a constant frequency. And then further and further you get higher frequency. So this one means it's a low pass filter. We're only passing through the low frequencies. And so this could be a Gaussian filter because Gaussian is low pass filter. It's for removing the noise. But on the other hand, while removing the noise, we are also sacrificing some of the detailed information. The edges, the tree structures become a bit blurry now. So yeah, so that's just an example of what we can do with filtering in the frequency domain. If you do this using the original spatial kernel, you should get the same result. It's just probably different speed of computation. Okay, so this is another example of why we want to do this. And previously, I actually briefly mentioned this with that example with 4 images. So I talked about superposition when you combine images in the input. Spatial domain is similarly in the frequency domain is a combination of different frequencies. So here is another example of this property. And it's probably a better example of why we really want to do frequency domain processing in some cases. So this one is called notch filtering. The objective here is we want to remove noise from this image. So it's a satellite image. Somehow you have this image, but you have all this noise. So that's called the scan line artifacts. So those like vertical lines or stripes across the image, and those are noise we want to filter out. So how we do this is if we consider frequency domain, we can first transform this into frequencies. So that will be the frequency 2D matrix representing this image. And in this one, somehow this line in the middle is representing the frequencies occurring in this region that are causing these noisy patterns. So if we know this, if we know this line corresponds to these noisy patterns, and that's what we want to remove, then we can just simply, based on this, we design this filter. So this filter means only the frequency components falling along this line will pass through, and others will be blocked. So that's called, because it's passing through, then it's called a notch pass filter. So if we have this filter, we can do multiplication in the frequency domain. And once after that, we can do an inverse Fourier transform into the spatial domain. And then that's the image you will get. So that means now we are only keeping the noise, removing all the other parts. And so if we want to get a clearer image, we can just subtract the noise from the image. So that's the notch pass filter. And we can also design an inverse of this. So that becomes the notch reject filter. So that means only this line is black, the other parts are passed through. And then if you do that multiplication, then inverse Fourier transform, you should just directly get this image. So yeah, so that's the effect of doing this frequency domain processing. You can pretty much get close to perfect result by using this kind of frequency targeted processing. But then of course, my question would be, how would you know these frequencies actually represent this noisy region, right? It's really not clear to me. So I think typically, either you have a way to measure what the frequency is, or it could be coming from some expert knowledge. They have this experience with this image acquisition device. They know that that's the frequency this device is causing. So then they know beforehand, that's the region you are looking at. Or if it's a computer scientist, maybe he has no background knowledge about this image acquisition at all, then I think that will need some just trial and error process to try to find out what the frequency component is. But eventually, if we do know that frequency corresponds to this region, we can design this filter, and the effect will be quite good. Okay, so that's just an example of how we can use frequency domain analysis. Okay. So here are some further concepts about the relationship between frequencies and how we want to use them. So, so the most important information is really in these 3 lines. So low-pass filter is to keep low frequencies but attenuate or remove high frequencies. And high-pass filter is the reverse. We want to keep high frequencies but attenuate low frequencies. And band-pass filter is in the middle. We want to keep the frequencies in the middle somewhere. This can be specified in a given band, and then we attenuate the rest. So all these concepts, these are not specific to images. If you have done signal processing, digital signal processing, it's all the same. So it's really nothing too special about images. Okay, so now we are back to Gaussian filter. We keep coming back to this because it's one of the best filters. It's very useful in many, many cases. So Gaussian, we have defined these equations during the last lecture. Here I just want to briefly show you what are the equations in the frequency domain. So we do have pretty nice looking equations for Gaussians. And from the equations, you will see they actually look not much too different. Although the details, the values, the amplitudes are different. But in the frequency domain, the Gaussian filters will still look like Gaussian functions, but of different frequencies and magnitude. So let me just show you this one first. So that's what it means. So in the spatial domain, we have this kind of Gaussian kernels. If we convert them into frequency domain, they will look like this. So they still look like Gaussian. And this is a difference of Gaussian kernel we talked about in the lab. So difference of Gaussian is just you subtract one Gaussian function from another. And typically, we subtract the one that has the, okay, we subtract the one with a bit higher sigma. That means a more spread out Gaussian function from the smaller sigma. So that's typically the way we do it. So what it means is this one is keeping more information. So it's doing some filtering, but not too much. So the output shouldn't be too blurry, but this one will be a lot blurrier. So you're removing more detailed information. So by subtracting this, we are essentially doing kind of a bandpass filter. So that means we are removing the very low frequency information, but also removing some of the very high frequency information and keeping the information in the middle. And if we look at the frequency domain representation, that's probably even clearer. So this is just symmetric. So if you look just this part, it means we are keeping the frequencies in the middle and removing the low part and the high part. So what's the advantage of this is, in some cases, the most important information we want to analyze is sitting within this middle range of frequencies. So that's why we want to do this. Okay, so back to the properties. This is the same slide as last week, but I just want to reiterate about some of them. So this one is like, yeah, so the Fourier transform of Gaussian is also a Gaussian function. So now it should be clearer why it's still a Gaussian. And then this one I also talked about last time. So that just means if we want to consider joint localization, that means we want to have narrow, for example, we want to have narrow Gaussian filters in both the spatial and frequency domain. That's just not kind of possible. There's always a trade-off, because like this one, if you have a really wide Gaussian, then you will have a narrower Gaussian in the frequency domain, and then reverse is true. Like this one is wider and this one is narrower. So we need a trade-off between how much information you want to keep, and the beauty with Gaussian is you can just vary the sigma term, and then check what's the output, especially in the spatial domain, I think. If you check the spatial domain and check whether that's kind of output you're expecting with a wide level of detailed information kept in the image. So if from your visual analysis you think that looks good, then that's probably how you want to proceed. Okay. So here are some examples. You will be using different image in the lab, but you probably get something similar. So the original, that's the image. And here I'm showing a smooth 1, smooth 2. That just means we apply 2 kernels. The first one is narrower, so that's less smooth. And then the second one is more smooth. So that means more blurry. And then you compute the difference. That should be the difference. And the second example is if you go, if you change the Gaussian function to be even wider, then you would have an even blurrier output. Then the difference will look like this. So if you compare this image with this one, you will see this one is highlighting the edges more sharply, right? So the changes are narrower. So that means we have better localization. This one is showing in the spatial domain. So we have better localization with this particular type of design of the Gaussian filter. And this one, because this is a difference, so you could minus this image from the original image, and then you will see you are removing a lot more information from the image, a lot more than necessary, because you might want to just remove certain edges if that's your objective, but now you are removing a lot more surrounding information as well. So similarly in the lab, I was asking, like, you could combine these 2 kernels into one kernel and do one convolution. but also you could do them separately. So what's the advantage of doing them separately? So it might not be that intuitive, because if you combine them, then you do one convolution. It's much more efficient. You have fewer computations. But if you do them separately, the advantage is you can see the intermediate effect. So intermediate effects are typically quite useful in computer vision for you to do analysis. You do, in many cases, you do need to look at what's the intermediate outputs in order to have a sense about whether the kernel, the design, specific design, whether they suit your objective. So that's the main advantage. Okay, so here is just a recap of, well, if we do this subsampling, upsampling, then we lose some information, and especially for the high frequency information. So hopefully through this lecture, this is getting clearer about why we are losing some frequency. And so this is kind of a separate concept about when we do the subsampling, then you have, that's the original image. You do one level subsampling, then you get a quarter of the size of the image. Then you can't keep going down. And so this kind of structure, multi-level representation of the same image, typically we call it an image pyramid. So it's kind of key word that you might see in computer vision studies. If you have anything like this, we will call it the image pyramid. And this is just an illustration about how we derive this image pyramid. So it's by having the input image, we can do a subsampling. So go down half, both row-wise and column-wise, so we get a quarter of the image. And so before we do the subsampling, we can do an approximation filter. That means typically a Gaussian filter, so to remove some noise. And then you do a downsampling. So that's the level, one level up or down, depending how you think about it. And so that's a quarter of the image. And based on this one, we can compute the residue between this image and this image. That means we want to measure how much information is lost through this process. So in order to get this, we will do upsampling from this one. So upsampling, now we get back the same size as the original image. Then we can just do a minus subtraction of the two images. Then you get the residue. And here is just, it just means doing the upsampling, we can also apply some filter to make the effect better. And so that's the residue. So if you keep doing this, repeating this, what you get is you are eventually representing this image with this pyramid, but what the intermediate ones are showing you are the residuals. So sometimes we like this kind of representation. So the intermediate ones are the residuals, and the most upper level, it doesn't have to go down to 1 by 1, that kind of degree. It's probably somewhere there. So that's the really small image representation of the original image. And that one will be keeping the most essential information. So because as you go down all this process, then you are losing more and more detailed information, but eventually you are keeping the most essential information. And then in the middle, you are keeping all the residuals. So if you want to go back from this image to the original image, then you can just keep doing the upsampling and some with the residue, and then gradually you will get back. So with this kind of pyramid, it's actually called the Laplacian pyramid. So I didn't really write down the term here, but it's a Laplacian pyramid. So that means the residuals, they will look like this. So they give you the differences between the downsample image and the original image. And at the smallest level, you keep the most essential information. Okay. So here's just an example about why this Laplacian pyramid is useful even nowadays. So we have this study about, essentially this is biopsy, so tissue biopsy. You have tissue biopsy and you can do it in many ways. So these are the two popular ways. One is smaller and also more cost efficient. The other one is even higher resolution. So both of the images, typically they are of gigapixels, super big images. And when you do processing, because they are so big, it takes lots of time. And we have to do patch-wise processing. That means one image will be typically divided into tens of thousands or even millions of image patches, and you do all the processing based on those patches. So the speed of processing is very important. And for this particular example, we were talking about how to transform or use generative adversarial network to do a generation from this image to just this image. So it's an image style transfer problem. So with this type of network, it's even slowly. It's very slow. So then our objective is how to make it faster. So in order to do this, a simple intuition is we just do downsampling, right? Because with smaller images, everything becomes faster. But then the smaller images, as we showed before, you are losing too much information. But typically with medical images, we do need to keep a certain level of details in order to not lose like cancer, tumor information. So that's why when we use Laplacian pyramid, we do the image transfer, that network training, using the smallest scaled image. And then gradually, in the middle, we add back the residual information. So with this process, we are almost keeping the important information as much as possible, but make the process a bit faster than if you just use the original image. So that's the intuition behind all this kind of image processing techniques. You might think they sounds very basic, nobody really uses them anymore, but in reality, we do use them still quite often. It's just we don't use them on themselves. They are typically always combined with some other more advanced methods. And this is just another example about frequency. So this is a typical wavelet transform of kind of frequency representation. So with wavelets, it's like Fourier transform, but with wavelets. So the outputs will be one image is converted into 4 images. So we have the LL means low, that means we have the lowest frequency representation of the original image. That's giving you the most information, the slowly varying information in the image. So that means the stable information, like that's another term. And then you have LH, HL, HH. So that's 3 channels of high frequency information in the image. And HH is typically really the more noisy part in the image. So now one image is converted into 4 images, and then you can do all sorts of processing on this. So typically we do separate processing based on the frequency information. So on low frequency, we do something different to the high frequency. And in this particular example, it's about adversarial perturbation. So that means, I think I mentioned in the first lecture, in computer vision, there's a specific problem called adversarial attack. That means you want to do some small modifications on the image to trick the classification model into classifying the image into a different result. So for example, this one, you might have a system to automatically recognize there's a hot air balloon there. But if you just modify a few pixels, then the system might think this one is like Apple, for example, anything. So it's possible, so that's like cybersecurity attack, that kind of systems. But if you do these perturbations on the image, if you are a good attacker, then your objective is you want to make sure the perturbed image look as similar to the original image as possible. You don't want to give the you don't want to reveal yourself that you are manipulating this image, right? So that's your objective. So in order to do that, people think if you find the highest resolutions, highest frequencies, then around that you do the image manipulation. That will give you very good result to trick the classifier, but at the same time, to a human eye, the image look almost the same as the original image. So that's the whole intuition behind it. We want to find out where the high frequency components are first, and then we change some pixels on the high frequency regions, and then you will have a perturbed image, but that looks the same as the original.
Sorry, just have a question. Like, do classifiers work by just checking the highest frequency, or like, is this doing something like filtering, checking the residual?
It's kind of relevant, because if you think about the convolutional neural network, it has many, many layers. So it's, typically we consider initially is looking at the high frequencies, because it's operating on small regions, and the filters are essentially like analyzing the edges. But gradually it will look at more and more higher information. Higher level, that means a more slowly varying, context information. So I think there will be some more details about this in week 7 and week 8. Not about this example, but about how the convolutional neural networks work. Okay, so this is just another example, not really about frequency, but about why we can integrate the filtering techniques with convolutional neural with deep learning. So in this example, it's called image implanting. So that means if you have an image, but some of the regions are missing for whatever reason, and you want to implant those regions, so you get back a naturally looking image. And to do this, this is a very famous study. So, and then it's actually quite intuitive, a simple framework. What it's talking about is in the middle, they are using this edge map as a ground truth to guide the image generation process. So that means that's the contours of the important information, important structures in the image, and then in the output, they want to have, they want to keep the contours, but filling in the information in the more smoother regions. So this one is, well, I'm not really describing the overall framework, but I'm just highlighting, in order to get this one, we just apply edge detection, right? So that's the techniques we talked about in the last lecture, where you can apply some kernels, do a filtering that gives you the edge information, and so that's simple, very simple image processing techniques you can apply to images and try to get these edge maps. And So although in the lecture we talk about simple filters, there are some other more complicated edge detection methods. But typically nowadays, those are standard library functions in OpenCV or some other libraries that you can use. Okay, so that's just an example. And yeah, all for this week. Next week, we will move on to feature extractions. So that's more like computer vision, how we extract features from the images first, and then we can apply classifiers typically to convert the features into certain interpretations from the images. Yeah, okay. That's all for this week.